Good evening and welcome to the live sessions for the course on computational science and engineering. It is 6 p.m. but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you. Good evening and welcome to week 7 of the live sessions for the course on computational science and engineering. This course is taught by Professor Ashok Dey, who is a member of the faculty of the Department of Aerospace Engineering at IIT Kanpur, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. So we are in the 7th week of the live sessions for this course, and I hope you have been having a good learning experience. Of course, Professor Day's lectures are more than sufficient to know the depths of the course and to gain a very good working understanding of the various aspects of computational science and how they apply to solving and modeling of engineering problems. The purpose of these live sessions are to act as a tutorial to supplement the exercises and the homework problems that are supplied with the course, and through solving a few illustrative problems to reinforce the key concepts that are supposed to be absorbed in the course of learning the course contents. In this week, we'll be mostly going over polynomial approximations and interpolations, and the motivation for this again stems from the fact that we are trying to have a numerical solution of a physical problem. A numerical solution may be exact, and that is to say that the error might be zero. However, in the general case, this will not be true. Uh, the error is zero only when we are having an analytical solution, and if we already have a simple closed form analytical solution, what is the need for computational solutions? So typically, a computational solutions will always have some error. However, the key takeaway is to minimize that error and to bring it to a scale which is small enough so that for all practical intents and purposes, uh, the solution that you obtain, though strictly somewhat erroneous, is still good enough. And that is why we are trying to approximate things. When we talk about polynomial interpolations, okay, so first, what is an interpolation, what is an extrapolation, and in what cases are they useful? Say, consider uh, a situation where you are given a few data points. It may be in the case of, say, X and Y data, where for certain input data X, you have the response of the system or the output function Y. And based on few such data points, say 3 or 5, you are asked to uh, estimate or to predict the nature and behavior of the system for any other input if the test input lies within the range, say among the data points that you have, x1, x2, x3, x4, there will be one which is the smallest and there is one which will be the largest. They form the range of the data set. If the test data set that you're given or the test data point that you're given lies within this range, that is to say if your data was between 0 and 5 and your test data is something like 3.7, if the test data lies within the range, it's called interpolation because you already have data on either extreme of the given data point, and you are just asked to you know, uh, test that assuming the data or the relationship which you are expecting or which you have predicted holds, what will be the response of the system at the test input. The other case, called extrapolation, is when you are trying to make predictions beyond the range of dataset which is provided to you. So to say, if the input dataset given to you is uh, 0 to 5, and if you're asked to predict the response of the system at the input of 10, this will be called extrapolation because now you are moving beyond the domain that you were originally working with. And The motivation for such polynomial approximations actually come from something called Weierstrass approximation theorem. And today I do not have access to my writing utilities. So what I've done is I have actually written all important things on the slides beforehand, and today we'll just be discussing them in great detail. Of course, I'll also be allowing you some time to say solve any example problems by yourself and to arrive at the solutions by yourself, so that this makes for a good learning experience. So first, the Weierstrass approximation theorem. Suppose that f is defined and continuous on closed AB. Now, for each epsilon greater than 0, there exists a polynomial p of x with the properties that the absolute value f of x minus p of x is less than epsilon for all x in closed A to B. Let us try to understand what this theorem is actually trying to convey. We have been given a range, or we have been given a domain which is closed A and B, or as you can see on this 2D plot here on the x-axis, we are working between the points A and B. In this domain, we are given that there is a function f which is defined throughout on this domain, as well as it is continuous. Continuous meaning that there is no point in this domain at which the function is not defined. So it is continuously defined at all possible points. So the function is continuous in this domain. Now we take a number epsilon. Typically these epsilons are very small, but of course the choice is completely arbitrary. It depends on you. And for any and all such epsilon which you may choose, which should be non-negative, sorry, which should be positive, greater than 0, and for the choice of any such function f, there always exists a polynomial p of x such that this will match very closely with your given function. We have y equals f of x in black and y equals p of x in blue, and we see that the absolute value of f of x minus p of x, that is the difference between the given function f of x and some polynomial p of x, will always be less than epsilon, or that it will always lie between the band. You have this black curve here which is y equals f of x. You displace it by plus epsilon and displace it by minus epsilon, so that on both sides you have an error of epsilon each. Now for any given domain, any given function and any choice of epsilon, there will always be a polynomial such as the one here, which is not exactly following the given function. It is even intersecting the function at a few points, but at other points it is differing, uh, say, significantly. Such a polynomial will always exist for all x in A to B. And the key takeaway from this is that while p of x is not really, say, an exact or is exactly equal to the given function f of x, it will lie within this band of plus epsilon and minus epsilon. If we were to make this epsilon or this error band smaller and smaller, smaller and smaller, then we can clearly see, such as for the dotted lines here, for this epsilon also, the Weierstrass approximation theorem guarantees that there will be some polynomial, maybe this time it is instead of p of x, it is some p1 of x, which will always lie within this band. And if we can make this epsilon very small but positive, we can be reassured that there will still be some polynomial which lies within this band. For a very small epsilon, the error from the given function f(x) is very small, and depending on the type of application needed, may even be insignificant or negligible. And then your approximate polynomial function p of x is a very good approximation of the given function of x. And this is the key idea that we'll build upon to derive and work with all the other polynomial approximations, and interpolations. Again, why polynomials of all mathematical constructs? It is very beautifully summarized here in this textbook by Burden and Fairs. One reason for the importance of polynomials is that they uniformly approximate continuous functions. By this we mean that given any function, such as f of x in the previous slide, which is defined and continuous on a closed and bounded interval, such as closed a to b in the previous slide, there exists a polynomial that is as close to the given function as desired. And what determines this closeness or proximity is the choice of this epsilon. If we choose to make this epsilon very, very, very small but positive, we can have a function which matches very, very well with the given function. So it is said that there exists a polynomial that is as close to the given function as desired. Another important reason, and this is on the implementation side, for considering the class of polynomials in the approximation of functions is that the derivative as well as the indefinite integral of a polynomial are easy to determine and are further also polynomials. And thus, for these reasons, polynomials are often used for approximating continuous functions. For a polynomial, say a naught plus a1x plus a2x square plus a3x cube, the derivative can be very easily calculated. The indefinite integral can also be very easily calculated. Further, both of these again are polynomials. Thus, if we are successful in approximating any given function using polynomials, we know that any further manipulation or any further, say, post-processing or further operations on these obtained functions will be very, very simple and computationally tractable compared to, say, the solutions of uh, other classes of functions such as hyperbolic, trigonometric, and so on. For these reasons, polynomials are often used for approximating continuous functions. And again, let us pay attention to the word approximating because, as we discussed at the outset of this session, we may be able to find the exact function if we are lucky, but outside some academic exercise or outside your test or some examination, it is highly unlikely that, say, in the modeling of a physical problem or a real world problem, we are able to guess or arrive at the very exact equation that governs such a problem. Of course, assuming that such an equation exists in the first place. Sometimes occurrences may be truly random, and there is no mathematical relationship which can help us predict the response of the natural system to any input that we may give to it. That is why we always say that we are approximating these continuous functions. That is, we are finding something which is approximately equal to the actual function with some error bound. Now we'll talk about the various types of polynomials which are used for interpolation and for approximation. First of these is called the Taylor polynomial. The Taylor polynomials agree as closely as possible with a given function at a specific point. It's very important to know this, at a specific point. However, because of this very good agreement of the Taylor polynomials with a given function at a particular point, their accuracy is also concentrated near this point, which is to say that far away from this point of choice, the accuracy of the Taylor polynomials may decrease significantly and the errors might be pretty significant. However, uh, just wisdom will suggest that a good interpolation polynomial needs to provide a relatively accurate approximation over the entire interval with which you are working and not really at one specific point. because typically in the solution of a physical problem, we are really interested in solving for the entire domain. The domain may be one dimensional, such as along a line, two dimensional, such as across a surface or a plane, or more commonly, three dimensional, that is in space. We want the solution of the system to be accurate, reasonably accurate throughout this domain and not really at any particular point. Of course, in some cases, the physics of the problem may be such that if we can get a good enough solution within some region of interest, that will suit our purpose. But then again, that region will also never be just one single point. It will always be at least a collection of, uh, or in 3D space, it will be at least some small volume. In 2D space, it will be some small area. It will never be just one single point. Since a good interpolation polynomial needs to provide a relatively accurate approximation over the entire interval, the Taylor polynomials are unsuitable as a good approximating polynomials because they concentrate their accuracy near a specific point. For the Taylor polynomials, all the information used in the approximation is concentrated at the single number x naught, which is our point of interest. So these polynomials will generally give inaccurate approximations as we move away from x naught, which is undesirable. And this truly limits Taylor polynomial approximation to the situation in which approximations are needed only at numbers close to x naught. For ordinary computational purposes, it is far more efficient to use methods that include information at various points. So Taylor polynomials may only be useful when, say, you have just one xy data point and you want to fit a polynomial to this data set. In which case, I mean, why are you even bothering with a polynomial? Because you can fit literally anything, a line, a point, a curve, a surface, a volume, everything can pass through that one point. But yeah, Taylor polynomials have limited applications as far as approximation of functions and interpolation and extrapolation are concerned. The second class of approximating polynomials that we'll deal with today are called Lagrange interpolating polynomials, and let us get familiarized with them. So, if x0, x1, x2 till xn are n plus 1 distinct numbers, and f is a function whose values are given at these numbers, then a unique polynomial px of degree at most n exists with f at x of k equals p at xk for each k equal to 0, 1, 2 to n. This polynomial is given by px equals f of x naught times l n comma 0 of x plus f of x1 times l n comma 1 of x plus till f of xn l of n comma n of x, where for each k going from 0, 1 to n, l n comma k of x, the Lagrangian, is given as x minus x naught x minus x1 till x minus xk minus 1 x minus xk plus 1 till x minus xn by xk minus x naught xk minus x1 times xk minus xk minus 1 xk minus xk plus 1 times xk minus xn. This might seem a little tortuous, but when we get down to actually solving a few examples, we'll find that this is simple enough. It's just that at the outset, the formula or the construction might appear a little bit challenging. And I have also solved an example here, which will help us be more familiar with the concept of Lagrange polynomials. Here we are asked to use the numbers, also called nodes, x0 equals 2, x1 equals 2.75, and x2 equals to 4 to find the second Lagrange interpolating polynomial for f of x equals 1 by x. Further, we are asked to use this polynomial to approximate f at 3 equals 1 by 3. Again, if we recollect, x0, x1 till xn are n plus 1 distinct numbers, and f is a function whose values are given at those numbers. In this case, we have x0, x1, and x2, and we will clearly notice that they are not equally spaced. So often, when we work with such data sets, we find that the x data are nicely, uh, say, equispaced. And maybe when we are writing a few computer programs for a numerical methods course or for our own code, when we are trying to make certain predictions, we might expect and design the code in a way that only accepts, say, equally spaced numbers or which works best with equally spaced data. But as we can clearly see, that need not always be the case. So I will just pause here for 1 minute and allow the participants to just go through the question and observe it and maybe try to solve it based on the formula that I presented on the previous slide. And after a minute, we'll get going with the solution. Okay, I hope you could start with the solution, but let us work through it. The numbers, also called nodes that were given are x0 equals to 2, x1 equals 2.75, and x2 equals 4. The function is also defined, given as f for x is equal to 1 by x. So for f at x0, this will become 1 by 2 or zero point 0.5. F at x1 becomes 0.36 recurring, and f at x2 becomes 0.25. Now we are asked to find the second Lagrange interpolating polynomial, and the reason for this is that we already saw that when we are given n plus 1 distinct numbers, we can construct a unique polynomial PS of at most n. Here we are given three such data points, so as to say n plus 1 is equal to 3, which implies that n is equal to 2. So what we can come up with is a second order Lagrange interpolating polynomial. If we go back to our formula, for any Ln comma k of x, L0 of x becomes simply x minus x1 x minus x2 by x0 minus x1 x0 minus x2, or 2/3 times x minus 2.75 times x minus 4. Similarly, for the function L1 of x, it will equal x minus x0 x minus x2 by x1 minus x0 x1 minus x2, which comes out to be minus 16 by 15 x minus 2 times x minus 4. Fairly simple. Now let us work out the function L2 of x. Again, from the given formula, this becomes x minus x naught times x minus x1 by x2 minus x naught times x2 minus x1, which will come out to be 2 by 5 times x minus 2 times x minus 2.75. Now that we have all of our Lagrange functions such as L0, L1 and L2, we can construct the Lagrange interpolating polynomial, the formula for which was again supplied in the slides in equation 3.1 here. It will simply be the sum of k equals 0 to 2 f of xk lk of x. And so the given Lagrange interpolating polynomial becomes the value of f at x naught is zero point 0.5 into L naught of x, which is 2/3 x minus 2.75 times x minus 4, plus f at x1, which is 0.36 recurring, or 4 by 11, times minus 16 by 15 times x minus 2 times x minus 4, plus f at x1, sorry, f at x2, which is 0.25, times 2 by 5 times x minus 2 times x minus 2.75. And when we multiply out the terms and simplify further, the final expression that we end up with for px equals 1 by 22 x square minus 35 by 88 x plus 49 by 44. Again, since we already know, for n plus 1 data points we can construct at most nth order polynomial. Here n plus 1 was 3, so we have a second order polynomial with the leading term x square. In the second part of this question, we are also asked to approximate f at 3 equals 1/3. We know the exact value, which will be simply 0.33 reckoning, and let us see what value the Lagrange interpolating polynomial gives us. So in the expression for the polynomial, we simply substitute x equals to 3 and compute it. So that will become 1 by 22 x square minus 35 by 88 x plus 14 by 44. Instead of x we write 3, so it becomes 1 by 22 3 square minus 35 by 88 times 3 plus 49 by 44, which comes out to be 0.32954. And so this is the predicted value, as we discussed in the previous session. Typically the predicted value will be denoted by, say, with a star. So here we are trying to approximate p. The predicted value will be p star. P star is 0.32954. The exact value p for the same number of decimal digits is 0.33333. The absolute error then becomes 0.379 into 10 power minus 2, and the relative error becomes 0.01 or 1.1%. So Lagrange polynomials are indeed a very powerful approximating technique, as well as fairly easy to construct. So it will be a very simple task to write a computer program for a Lagrange interpolating polynomial, which can help us approximate a given function. Again, by interpolation, what we mean is that, say here we had x naught equals to 2, x naught equals to 2.75 and x2 equals to 4. We were working on the domain closed 2 to 4. However, we do not have any information about, say, the value of the function at number, say, at 3.9. We can compute it using the interpolating function that we have, and that is what we exactly did. We tried to find the value at 3, that is, we were interpolating, and saw that the value predicted by the Lagrange interpolating polynomial was in fairly good agreement, only 1.1% apart from the exact solution. However, this is a very simplified example. And typically in the solution of an actual physical problem, you'll find that things can get fairly more complicated. The next concept we'll discuss today is the concept of divided difference. And here in the slides, we have a few definitions which will be very handy for further referral. The zeroth divided difference of the function f with respect to xi, also denoted as f with xi in square brackets, is simply the value of f at this given point xi. So the zero divided difference f at xi is simply equal to f of xi. The remaining divided differences are defined recursively. The first divided difference of f with respect to xi and x plus 1 is denoted by f with xi comma xi plus 1 within square brackets and defined as f of xi comma xi plus 1 equals f of xi plus 1 minus f of xi by xi plus 1 minus xi. The reason it is mentioned that these things are defined recursively is because for the definition of f of xi comma xi plus 1, we need the definition of xi plus 1, which is given in the previous step. Similarly, for the definition of f at xi, xi plus 1 and xi plus 2, we will need the definition of f of xi plus 1, xi plus 2, which will require definition 3.8, which will again borrow from definition 3.7. So we are uh, going back a few steps and calling the previous functions, which as we all know is called recursion. Similarly, after the k minus first divided differences, the kth divided difference relative to xi, xi plus 1, xi plus 2 and xi plus k is given as f at xi, f of xi, xi plus 1, xi plus k minus 1, xi plus k is equal to f of xi plus 1, xi plus 2, xi plus k minus f of xi, xi plus 1, xi plus k minus 1 by xi plus k minus xi. That's given in equation 3.9. And the process of computing these divided differences will end with the single nth divided difference given here, f of x naught x1 xn is equal to f of x1 x2 till xn minus f of x naught x1 till xn minus 1 by xn minus x naught. Now let us suppose that Pn of x is the nth Lagrange polynomial that agrees with the function f at the distinct numbers x0, x1, x2 till xn. While this polynomial is unique, there are alternate algebraic representations that are useful in certain situations. The divided differences of f with respect to x0, x1, x2 till xn are used to express that same Lagrange interpolating polynomial Pn of x in the form Pn of x is equal to a0 plus a1 times x minus x0 plus a2 times x minus x0 times x minus x1 plus an times x minus x0 x minus x1 till x minus xn minus 1. And here we have the definitions. A0 equals f of x0, a1 equals f of x0 comma x1, and then we further define the other terms recursively to end up with the Lagrange interpolating polynomial but in a different form. Now, how do you evaluate the constants a0 and a1? It is fairly all the constants a0, a1, a2 till ak. It is simply the value of these divided differences for each k. Thus, Pn can be rewritten in a form which is called the Newton's divided difference. Pn of x is equal to f of x naught plus summation k equals 1 to n f of x naught x1 x2 till xk times x minus x naught x minus x1 x minus x2 till x minus x k minus 1, and the value of the divided difference f of x0, x1, x2, xk is independent of the order of the number x0, x1, x2, and so on. Thus, order is not important in the calculation of these divided differences. We also have a useful tabular form to easily understand and work with these divided differences. In the first column, we have the domain, the numbers x, such as x0, x1, x2 till x5. Then we have the zeroth divided difference, which is simply the value of the function at that point. So f of x0, f of x1, and so on till f of x5. Next, we must find the first divided difference, which makes use of both f of x1 and f of x0. Then we must calculate the second divided differences, which makes use of the first divided difference f of x1 comma x2 minus f of x0 comma x1, and similarly other terms. Finally, we find the third divided differences, and it is possible to keep going on further till, in this case, the fourth and the fifth divided difference, because we had 6 points that we are working with. Now, we'll also try to solve a numerical based on the formula supplied in the slides. We're asked to generate the divided differences for the given data and construct the interpolating polynomial that uses this data. And I will allow the participants a minute to absorb the question and to start working with the formula provided, and then we'll work out the entire solution. So let us start working through the solution. The data set that has been supplied to us consists of x and f of x. Here the points are 1.0, 1.3, 1.6, 1.9, and 2.2, so they are equally spaced. And we also have the value of the function f of x to each of these points. As we very well know, the zeroth divided difference is simply the value of the function at each of these points. And so it's like the zeroth divided differences are already provided to us. And here we have 5 points, so we will construct a fourth order function as we already saw. For the set of first divided differences, let us compute a few, and I'm pretty sure we will be able to calculate the others by using the formula provided. So for the first divided difference of x0 and x1, f of x0 and x1 is equal to f of x1 minus f of x0 by x1 minus x0, which comes out to be 0.6200860 minus 0.7651977 by 1.3 minus 1.0, or minus 0.4837057. Similarly, for the for the first divided difference of x1 and x2, this is simply equal f of x2 minus f of x1 by x2 minus x1, that is 0.4554022 minus 0.6200860 by 1.6 minus 1.3, which comes out to be minus -0.548946. Similarly, the other first divided differences can be calculated for x2 and x3 and x3 and x4. Now let us try to calculate the second divided differences. Again, in which case we'll make use of the first divided differences, which in turn were calculated using the zeroth divided difference. So the second divided difference, f of x0, x1 and x2, is equal to f of x1, x2 minus f of x0, x1 by x2 minus x0, which equals -0.5489460 minus 0.483757 by 1.6 minus 1.0, which comes out to be negative 0.1087338. Similarly, we can find one more second divided difference, this time for x1, x2 and x3, and the formula is fairly straightforward. This equals f of x2 x3 minus f of x1 x2 by x3 minus x1 comes out, comes out to be minus 0.5786120 minus 0.548946 by 1.9 minus 1.3, which comes out to be minus 0.049443. Then we find the two third divided difference terms, f of x0, x1, x2, x3 is equal to f of x1, x2, x3 minus f of x0, x1, x2 by x3 minus x0, which equals minus 0.049443 minus 0.1087338 by 1.9 minus 1.0, which equals 0.0658783. Finally, we will have only a single fourth divided difference term, f of x0, x1, x2, x3, x4, and this comes out to be 0.0018251. But again, I will request the participants to verify this answer, as since the calculation of these terms requires a lot of calculations, it is entirely possible that I might have made small mistakes in the solution, and the final result that you get might be differing from the one that I have arrived at. It does not mean that your answer is wrong, but I might have made some calculation error, and so I request you to kindly verify the solutions. Now, with all the divided difference terms found, we can have the interpolating polynomial in this fashion. P for x, or the polynomial of the fourth order, equals 0.7651977 minus 0.483757 times x minus 1 minus 0.1087338 x minus 1 x minus 1.3 plus 0.06587883 times x minus 1 x minus 1.3 x minus 1.6 plus 0.0018251 times x minus 1 x minus 1.3 x minus 1.6 times x minus 1.9. Again, this interpolating polynomial is not different. In fact, the Lagrange interpolating polynomial for a given data set is unique. However, this is just a different representation of the same polynomial. And as we started doing in the previous session, we'll also try to write a pseudocode for Newton's divided difference formula. And as I had spoken in the previous session, the reason we are working with a pseudocode and not an actual code is because an actual code will be restricted by the semantics and syntax of the programming language of your choice. A program that is written in C++ will have a syntax which is significantly different from one that is written in Python or in Fortran. However, we're not really bothered about the code or the actual structure or the language of choice for writing these programs. What we're really bothered with is developing an understanding of the algorithm and the solution strategy behind these techniques. That is why we make use of pseudocodes, which are actually just snippets of logical statements, which are in a human readable language and which help us, say, identify the exact solution steps, right, using such a solution scheme, such as the Newton's divided difference formula. In the writing of a pseudocode for this Newton's divided difference formula, the input would be the numbers x0, x1, x2 till xn, and the values of the function at x0, x1, x2, and till xn. And here we can have them input in some special form, such as f00, f10, fn0, and so on. The reason for this particular choice will be clear once we delve further into this pseudocode. And what we'll desire from such a pseudocode is to output the uh, Lagrange interpolation function in the Newton's divided difference form. In the first step, we start a loop for I equals 1, 2, 3 till n, then a nested loop for j equals 1, 2, 3 till I. We find these Newton's divided difference terms recursively, and so set f I comma j equals fi j minus 1 minus fi minus 1 j minus 1 by xi minus j. We output these divided difference functions as f00, f11, f22, fnn, and so on, and stop. And that's it. It was just a two-step pseudocode. I hope the participants are trying and implementing the pseudocode that we share in these tutorial sessions. Just like the divided difference, there is also something called a forward difference. And the Newton forward difference formula is constructed by making use of the forward difference notation delta, introducing Aitken's delta square method. If you are not familiar with it, I request that you just Google it and go through some preliminary material. Now, the first divided difference, f of x naught comma x1 equals f of x1 minus f of x naught by x1 minus x naught is equal to 1 by h, or where h is often referred to as the step size, f of x1 minus f of x naught, or 1 by h delta f of x naught. Similarly, for the second divided difference, f of x naught, x1, and x2, this becomes equal to 1 by 2h times delta f of x1 minus delta f of x naught by h, which equals 1 by 2h square del square f of x naught. And in general, for the kth divided difference, this will become f of x naught, x1, x2 till xk is 1 by k factorial h power k delta power k f of x naught. The Newton's divided forward difference formula written using such a notation is simply equal to Pn of x equals f of x naught plus summation k equals 1 to n, combination of s and k del power k f of x naught. Just like the forward difference, there is also something called the backward difference. And the way to understand it is if the interpolating nodes are reordered from last to first as xn, xn minus 1, xn minus 2 till x0, we can write the interpolatory formula in the given fashion. Pn of x equals f of xn plus f of xn comma xn minus 1 times x minus xn plus f of xn x minus 1 xn minus 2 times f of x minus xn x minus xn minus 1, and so on. If in addition the nodes are equally spaced with x equals xn plus sh and x equals xi plus n s plus n minus I times h. Then Pn of x equals Pn of xn plus sh, which becomes equal to f of xn plus s times h times f of xn minus 1 plus s times s plus 1 times h square times f of x1 is 1 x1 is 2 and so on till s times s1 is s plus 1 times s plus 2 plus s plus n minus 1 times h power n times f of xn x1 x2 xn xn minus 2 xn minus 2 till x naught. After this exercise, what we'll end up with is Newton's backward difference formula, which gives us another expression for the Newton or Lagrange interpolating polynomial. Pn of x equals f of xn plus summation k equals 1 to n minus 1 power k combinations of minus s and k nabla power k f of xn. And after the forward difference and the center difference and the backward difference, we come to what is called the center difference form and Stirling's formula.
Wooden patta is there.
The Newton forward and backward difference formulas are not appropriate for approximating effects when x lies near the center of the table. That is to say, we had these data points that were given to us, and we will use this for interpolation, that is to find the value of the function at some previously unknown data point or some previously not investigated data point. However, the Newton's forward and backward difference formulas are not appropriate for the case when this unknown data point lies near the center of the table, because then neither will permit the highest order difference to have x naught close to x. A number of divided difference formulas are available for this case, each of which has situations when it can be used to maximum advantage. These methods are known as centered difference formulas, and here we will consider one of them called Stirling's formula. So, for the centered difference formulas, we choose x naught near the point being approximated and label the nodes directly below x naught as x1, x2 till xn, and those directly above as x minus 1, x minus 2, and so on. And with this convention, the Stirling's formula is given by equation 314, and depending on whether the number of terms n is or the number of data points n is odd or even, we will have a slight difference in the formula. The next topic that we will discuss is called Hermite polynomials. And a little background. Oscillating polynomials generalize both the Taylor polynomials and the Lagrange polynomials. Suppose that we are given n plus 1 distinct numbers x0, x1, x2 till xn in closed AB and non-negative integers m0, m1 till mn, and m be defined as the maximum of this set of m0, m1, m2 till mn. The oscillating polynomial approximating a function f which is m continuous on AB at xi for each I equals 0, 1, 2 till n is the polynomial of least degree that has the same values as the function f and all its derivatives of order less than or equal to mi at each xi. The degree of this oscillating polynomial is at most given by the sum of mi for I equals 0 to n plus n. Let x0, x1, x2 till xn be n plus 1 distinct numbers in closed AB, and for I equals 0, 1, 2 till n, let mi be a non-negative integer. Let us suppose further that f belongs to m continuous, f is m continuous on closed AB, where m is maximum of 0 less than equal to I less than equal to n mi. Then the oscillating polynomial approximating f is the polynomial px of least degree such that the condition that is to be satisfied is that dk dxk of p of xi equals dk dxk of f of xi for each I equals 0, 1, 2 till n and k 0, 1, 2 till mi. Now for the particular case where f is first continuous on closed AB and x0, x1, x2 till xn belong to closed AB are distinct, and the unique polynomial of least degree agreeing with f and f prime at all these numbers x0, x1, x2 till xn is the Hermite polynomial, and it is the Hermite polynomial of degree at most 2n plus 1. The formula for which is given by h 2n plus 1 of x equals summation j equals 0 to n f of xj h n comma j of x plus summation j equals 0 to n f prime of xj h hat n comma j of x, where for l n comma j of x denoting the jth Lagrange coefficient polynomial of degree n, we have hn comma j of x equals 1 minus 2 times x minus xj l prime n comma j of xj times L square nj of x, and h hat nj of x equals x minus xj L square n comma j of x. Furthermore, if f is 2n plus 2 continuous on closed AB, then fx is equal to h 2n plus 1 times x. Note that this is 1 less than the continuity requirement on f, plus x minus x naught square, x minus x1 square times x, so on till x minus xn square by 2n plus 2 factorial. 2n plus 2th derivative of f times zeta of x, xi of x for some unknown xi in the interval open AB. And that was a lot of theory, but we'll just solve one illustrative example which will help make the concept of Hermite polynomial very easily perceptible. But before that, let us take a short break. When we return, we'll start by solving this illustrative example. Let's continue our session. We were discussing the solution of this question, where we are asked to determine the Hermite polynomial which agrees with a given set of data or fits this given set of data to find an approximation for the interpolated point 1.5. Again, we note that here we are supplied 3 points, uh, that is k01 and 2, and 3x is 1.3, 1.6, and 1.9. Since n plus 1 is 3, n comes out to be 2, and so we will have a second order Lagrange polynomial in this case. L2, 0 of x will come out to be x minus x1, x minus x2 times x naught minus x1, x naught minus x2, and if you substitute the given data, it will become x minus 1.6 times x minus 1.9 by 1.3 minus 1.6 times 1.3 minus 1.9, which equals 50 by 9 times x minus 1.6 times x minus 1.9, which gives us the polynomial 50 by 9x square minus 175 by 9x plus 152 by 9. If we take its derivative to find L prime 2, 0 of x, it will simply come out to be 100 by 9x minus 175 by 9. Similarly, we must find the Lagrange polynomial L2, 1 of x, which comes out to be x minus x naught, x minus x2 times x minus x1 by x1 minus x naught, x1 minus x2, and substituting the values given to us, this becomes x minus 1.3 times x minus 1.9 by 1.6 minus 1.3 by 1.6 minus 1.9, and this will come out to be minus 100 by 9x square plus 320 by 9x minus 247 by 9. The derivative L prime 2, 1 of x will become minus 200 by 9x plus 320 by 9. Similarly, for the third Lagrange polynomial L2, 2 of x, the formula for which is x minus x naught, x minus x1 by x2 minus x naught, x2 minus x1, where if we substitute the values given to us, it becomes x minus 1.3 times x minus 1.6 by 1.9 minus 1.3 times 1.9 minus 1.6, which finally comes out to be 50 by 9x square minus 145 by 9x plus 104 by 9. The derivative L prime 2 of x becomes 100 by 9x minus 145 by 9. Now that we have calculated all of these Lagrange polynomials, we are ready to find the Hermite polynomial functions. We start by finding h2, j of x, then we'll find h hat 2, j of x. h2, 0 of x is simply 1 minus 2 times x minus 1.3 times minus 5, which comes out to be times 50 by 9 x square minus 175 by 9 times x plus 152 by 9 square. Note that we are making use of the Lagrange polynomials that we calculated in the previous steps. Upon simplification, this becomes 10x minus 12 times 50 by 9 x square minus 175 by 9x plus 152 by 9 whole squared. Similarly, the Hermite polynomial h2, 1 of x, which becomes equal to 1 times minus 100 by 9x square plus 320 by 9x minus 247 by 9 whole square, and h2, 2 of x, which equals 10 times 2 minus x times 50 by 9x square minus 145 by 9x plus 104 by 9 whole square. Again, make note that these functions are simply the Lagrange functions, Lagrange interpolating functions, or Lagrange polynomials that we already found in the previous steps. Now we find the functions h hat 2, j of x, the first of which h hat 2, 0 of x is equal to x minus 1.3 times 50 by 9x square minus 175 by 9x plus 152 by 9 whole square. H hat 2 comma 1 of x equals x minus 1.6 times minus 100 by 9x square plus 320 by 9x minus 247 by 9 whole square. And h hat 2 comma 2 of x is equal to x minus 1.9 times 50 by 9x square minus 145 by 9x plus 104 by 9 whole square. The order of the Hermite polynomial as opposed to the order of the Lagrange polynomial that we were calculating is equal to 2n plus 1. Again, n plus 1 is the number of data points supplied to us. N plus 1 is 3, so n is 2. The order of the Hermite polynomial thus becomes 2n plus 1 is equal to 5. And the fifth order Hermite polynomial for this case is equal to h5 of x is equal to 0.6200860 h2 comma 0 of x plus 0.4554022 h2 comma 1 of x plus 0.2818186 h2 comma 2 of x minus 0.5220232 h hat of 2 comma 0 x minus 0.5698959 h hat 2 comma 1 of x minus 0.5811571 h hat 2 comma 2 of x. After finding this Hermite polynomial, we were also asked to find an approximation at x equals 1.5 or to interpolate at x equals 1.5. And for this case, using the Hermite polynomial of fifth order, it comes out to be 0.5118277. Once again, I request the participants to verify this answer. And I figured that the formula for a Hermite polynomial was not as simple or straightforward as for something like, say, the Lagrange interpolating polynomial or the Newton divided difference formulation. And so I further decided to supply the pseudocode for this case. Please note that this code is not written by me, rather I have borrowed it from reputable sources and I verified that it works correctly. So for such a pseudocode for a Hermite interpolation, the input would be the numbers x0, x1, x2 till xn and the values of the functions at all of these. So f of x0, f of x1 till f of xn. We'll also need the derivatives f prime at x0, f prime at x1, f prime at x2 and so on till f prime at xn. The output for such a pseudocode would be the numbers q of q0, 0, q1, 1, q2, 2 till q2n plus 1, q2n plus 1, where the Hermite polynomial of 2n plus 1th order h of x is equal to q00 plus q11 x minus x0 plus q22 x minus x0 square plus q33 x minus x0 square x minus x1 and so on till q2n plus 1 2n plus 1 x minus x0 square x minus x1 square x minus x2 square till x minus xn minus 1 square times x minus xn. The first step is to start the loop setting I equal to for I equals 0 1 till n, do steps 2 and 3. In the second step we set z2i equals x of I, z2i plus 1 equals x of I and q2i comma 0 equals f at xi, q2i plus 1 comma 0 equals f of xi and q2i plus 1 comma 1 equals f prime at xi. In the third step, if I is not equal to 0, then we set q of 2i comma 1 equals q 2i comma 0 minus q 2i minus 1 comma 0 by z of 2i minus z of 2i minus 1. In the fourth step, we start another loop. The previous loop was supposed to only loop through steps 2 and 3. So for I equals 2, 3 till 2n plus 1 and a nested loop for j equals 2, 3 till I. We set qij equals qi comma j minus 1 minus qi minus 1 comma j minus 1 by zi minus zi minus j. And in the fifth and final step, we simply output all of these coefficients of the Hermite polynomial of the nth 2n plus 1th order, which are q00, q11, q22 till q2n plus 1, q2n plus 1. Then we make the program stop. The next concept that we'll be talking about today is of piecewise interpolation. Excuse me a moment. Till now, what we were discussing was the approximation of any arbitrary function on closed intervals using one single polynomial. However, high degree polynomials can oscillate erratically, that is, a minor fluctuation over a small portion of the interval can induce large fluctuations over the entire range. But then again, we do not really need to have this one master function which can fit uh, throughout the domain. We can in fact have piecewise interpolations where we have a function for a particular subset of the domain, another function for the next subset, and we have some condition so that the two functions agree on the value of the function at the boundaries of these subsets. And this is precisely what is called piecewise polynomial approximation. So, in this piecewise polynomial approximation, the approach is to divide this approximation interval into a collection of subintervals and construct a generally different approximating polynomial on each subinterval. The simplest piecewise polynomial approximation is piecewise linear interpolation, which consists of joining a set of data points x0, f of x0, x1, f of x1, and so on till xn, f of xn by a series of straight lines as shown in the figure to the right. However, a clear disadvantage of linear function approximation is that there is likely no differentiability at the endpoints because there is a sharp change in the slope. And in a geometrical context, this typically means that the interpolating function is not smooth. Often, it is clear from physical conditions that smoothness is a requirement, so the approximating function must be continuously differentiable. That is, it should not have the sharp spikes. And this is where we get introduced to the concept of cubic spline interpolation. The most common piecewise polynomial approximation uses cubic polynomials between each successive pair of nodes and is called the cubic spline interpolation. A general cubic polynomial involves four constants so that there is sufficient flexibility in the cubic spline procedure to ensure that the interpolant is not only continuously differentiable on the interval but also has a continuous second derivative. So for defining a cubic polynomial, we would typically have a naught. It is typically equal to a naught plus a1x plus a2x square plus a3x cube. And that's why you have these four constants. Not only is the cubic function itself uh, continuously differentiable, it also has a continuous second derivative. Given a function f defined on closed AB and a set of nodes a equals x0 less than x1 less than x2 less than xn equal to b, a cubic spline interpolant S for this given function f is in turn a function which satisfies the following six conditions. The first condition being S of x is a cubic polynomial denoted Sj of x on the subinterval Sj, Sj plus 1 for each j equals 0, 1, 2 till n minus 1. Sj at xj is equal to f of xj, and Sj at xj plus 1 is equal to f of xj plus 1 for each j equal to 0, 1, 2 till n minus 1. Sj plus 1 of xj plus 1 is equal to Sj of xj plus 1 for each j equal to 0, 1, 2 till n minus 2. As we were discussing, the value of the function at any given point must be the same whether we approach it from the left or the right, which is basically the continuity requirement. S prime j plus 1 at xj plus 1 is equal to S prime j at xj plus 1 for each j equals to 0, 1, 2 till n minus 2, which is the differentiability requirement. That is, the slope uh, at a point should be the same whether we approach it from the left or from the right. The fifth condition is that S double prime j plus 1 xj plus 1 is equal to S double prime j at xj plus 1 for each j equals 0, 1, 2 till n minus 2. That is, the derivative of the slope should also be continuous, and one of the following sets of boundary conditions has to be satisfied. Either it is S double prime at x naught is equal to S double prime at xn is equal to 0. That is, the second derivative of the function is 0. Such a cubic spline is referred to as a natural or free boundary, and S prime at x naught is equal to F prime at x naught, and S prime at xn equals F prime at xn, which is known as the clamped boundary or the clamped cubic spline. What is the physical interpretation of these two cases? A natural spline has no conditions imposed for the directions at its endpoints, so that the curve takes the shape of a straight line after it passes through the interpolation point nearest its endpoints. The name derives from the fact that this is a natural shape a flexible strip assumes if forced to pass through specified interpolation points with no additional constraints. That is why it's called natural or free. Clamping a spline indicates that the ends of the flexible strip are fixed so that it is forced to take a specific direction at each of its endpoints. This is important, for example, when two spline functions should match at their endpoints. This is done mathematically by specifying the values of the derivative of the curve at the endpoints of the spline. In the fifth question for today, we will construct a natural cubic spline that passes through the points 1, 2, 2, 3, and 3, 5. Again, the natural cubic spline would implies that there is this hidden condition where the second derivative at x naught is equal to the second derivative at xn, which is equal to 0. That is the slope of the interpolating spline. The two endpoints of the domain will be equal to 0. So let us take a moment to review these conditions, and then we'll start solving the uh, construction of the cubic spline interpolation problem. Let us now proceed with the solution. Now we are interpolating and we are doing a piecewise interpolation. So we have these three data points 1, 2, 2, 3, and 3, 5. We will construct one cubic spline uh, between the points 1, 2, and 2, 3, and a second cubic spline between the points 2, 3, and 3, 5. Now each of these cubic splines will have four coefficients or four constants to be determined. H0 of x equals a naught plus b naught x minus 1 plus c naught x minus 1 square plus d naught x minus 1 cube, and s1 of x equals a1 plus b1 x minus 2 plus c1 x minus 2 square plus d1 x minus 2 cube. Of course, the terms x minus 1 and x minus 2 are coming from the fact that our domain has these 3 points 1, 2, and 3. We are trying to fit one cubic span between the domain points 1 and 2, and second cubic span point between the domain points 2, 3, 2 and 3. Now, for the first cubic span S0, we start by satisfying each of the conditions that we have. So f of 1 equals 2 is equal to a naught, f of 2 is equal to 3 is equal to a naught plus b naught times 2 minus 1 plus c naught times 2 minus 1 square plus d naught times 2 minus 1 cube. So we are trying to solve for the four coefficients, and this is pretty similar to what we have been doing even in the previous sessions, whether say it was the decomposition of any given function into partial fractions or using the cover-up method or comparing coefficients. So this exercise is fairly straightforward, and we will have to find four conditions to solve for the four unknowns. We already found by substituting the boundary condition f of 1 that a naught is equal to 2, and we found that the sum a naught plus b naught plus c naught plus d naught is equal to 3. Now for the second cubic spline, we can again insert one more condition, that is the value of the function at x equal to 2, which is equal to 3. This gives us a1 equal to 3 and f at x comma 3 equal to 3 is equal to 5, which gives us that 5 equals a1 plus b1 plus c1 plus d1. What about the other conditions to find these numbers? We have additional conditions implicitly built into the problem based on the type of the end boundary conditions that were specified. In this case, it was a natural cubic spline, which suggests that the slope of the cubic spline at the endpoints of the entire domain will be 0. So S prime, S naught prime at 2, this is the continuity requirement of the first derivative at the meeting point. We had the three domain points 1, 2, and 3. At point 2, the slope of the functions should be the same whether we approach it from the left or the right. So S naught at 2 is equal to S1 prime at 2, which gives B naught plus 2C naught plus 3D naught is B1. From the requirements of the second derivative, S0 double prime x equals to 2 equals S1 double prime x equal to 2, which gives 2C naught plus 6D naught is twice C1. From the free boundary condition, S naught double prime at x equal to 1 is 0, which gives C naught equal to 0. And from the free boundary condition for the second cubic spline, S1 double prime at x equals to 3 is 0, which gives 2C1 plus 6D1 equal to 0. Now with all of these equations, we are able to solve, we have 8 unknowns and 8 equations. So we can solve uniquely for each of the unknown coefficients. This gives us A naught is 2, B naught is 3 by 4, C naught is 0, D naught is 1 by 4, A1 is 3, B1 is 3 by 2, C1 is 3 by 4, and D1 is 1 by 4. So A naught plus B naught times x minus x naught plus C naught times x minus x naught square plus D naught times x minus x naught cube, it becomes equal to 2 plus 3/4 times x minus 1 plus 0 times x minus 1 square plus 1/4 times x minus 1 cube. Similarly, the second cubic spline S1 was originally equal to A1 plus B1 times x minus x1 plus C1 times x minus x1 square plus D1 times x minus x1 cube becomes 3 plus 3 by 2 times x minus 2 plus 3/4 times x minus 2 square plus 1/4 times x minus 2 cube. Thus, the piecewise approximating function s of x becomes equal to s naught of x for x belonging to 1 comma 2 and equal to s1 of x for x belonging to 2 comma 3. So in the domain 1 comma 2 it becomes 2 plus 3/4 x minus 1 plus 1/4 x minus 1 cube, and in the interval 2 comma 3 it becomes 3 plus 3 by 2 x minus 2 plus 3/4 x minus 2 square plus 1/4 x minus 2 cube. Again, let us further complete our understanding of these natural cubic splines by writing a pseudocode for the same. Such a pseudocode would need the following input: n, that is the number of data points, x0, x1, x2 till xn, a0 equals f of x0, a1 equals f of x1 till an equals f of xn, and it will give the output aj, bj, cj, dj for j equals 0, 1, 2 till n minus 1. These are the coefficients for all the various piecewise interpolating functions that we need. S of x is equal to sj of x is equal to aj plus bj times x minus xj plus cj times x minus xj square plus dj times x minus xj cube for xj less than equal to x less than equal to x j plus 1. In the first step, we start our loop. For I equals 0, 1, 2 till n minus 1, we set h of I equals xi plus 1 minus xi. In the second step, for I equals 1, 2, 3 till n minus 1, we set alpha I equals 3 by hi times ai plus 1 minus ai minus 3 by hi minus 1 times ai minus ai minus 1. In the third step, we set L0 equal to 1, mu 0 equal to 0, and Z0 is equal to 0. And if we suddenly wonder where these terms L0, mu 0, and Z0 came in, these are actually terms we are familiar with from the solution of the tridiagonal linear system using the tridiagonal matrix algorithm. Now, for I equals 1, 2, 3 till n minus 1, we set Li equals twice xi plus 1 minus xi minus 1 minus hi minus 1 mu I minus 1. We set mu I equals hi by li, and we set zi equals alpha I minus hi minus 1 times zi minus 1 whole divided by li. In the fifth step, we set ln is equal to 1, zn is equal to 0, and cn is equal to 0. In the sixth step, we set j equals n minus 1. We start the loop for j equals n minus 1, n minus 2, n minus 3 till 0. We set Cj equals 2j minus, sorry, equals Zj minus mu j times Cj plus 1. Bj equals Aj plus 1 minus Aj by Hj minus Hj times Cj plus 1 plus 2Cj by 3. Dj equals Cj plus 1 minus Cj by 3Hj. And finally, in the seventh step, we output all of these coefficients Aj, Bj, Cj, and Dj for the required number of piecewise cubic spline interpolating functions j equals 0, 1, 2 till n minus 1, and stop the program. So in today's session, we'll only be discussing till the natural cubic spline, and if time permits, maybe we will take up the clamped cubic spline interpolation in the next session. Of course, it is not very different apart from the slope requirement on the extreme edges of the overall interval. Thus, it simply involves changing two or more conditions in the solution process. And that brings us to the end of today's live session. This was week 7 of the live sessions for the course on Computational Science and Engineering. I am Sourav Goswami from IIT Bombay. I thank you for tuning in and I hope to see you again in the next session, which I guess is the session for week 8 and the final session for this course. Thank you very much.